This video will cover using ridge regression and the elastic net in R. By the end of this video, you should understand how you train ridge regression and elastic net models in R, what methods are available to help you choose a good value of the regularization parameter lambda in these modeling tools, and how you set the value of the mixing parameter alpha in the elastic net. The R code used in this video is available in the learning management system. You'll need the data file dcelectricity.rds if you'd like to follow along. The R package glmnet utils can also train ridge regression and elastic net models. It uses the glmnet function, just like lasso. You can set a value of the mixing parameter with the argument alpha equals. If you set alpha equals to 1, you get the lasso, which is the default. If you set alpha equals to 0, you get ridge regression, and any other value in between would be an elastic net regression. Just like with lasso models, training ridge regression and elastic net models requires that you choose a value of the regularization parameter lambda. You can determine an optimal value using cross-validation. Just like lasso, you can use the cv.glmnet function. All you'll have to do is set the appropriate level of the mixing parameter with the alpha equals argument. So we'll get started training a ridge regression model in R. We'll load the dcelectricity.rds data file, and just like before, we'll divide it into training and test samples using the sample function. So looking at my R code, you've seen all this before. We'll load all the appropriate libraries, including the glmnet utils library. We'll also use model R and Broom. I'll load the sample data, then divide it into two data sets, a training and a test data set, using the sample function. I'll just run all of that now. And looking in the Environment Explorer, you can see that I have loaded these data files and split them into training and test data. Now that we've created our training data, let's train OLS, lasso, and ridge regression models using the following formula. The label demand is going to be a function of 10th order polynomials of the feature high temperature, a 10th order polynomial of the feature low temperature, and the two-way interaction of all the terms in those polynomials. We'll compute the root mean square error for the OLS model using tenfold cross-validation, and we're going to plot the cross-validated mean square error for the ridge regression model on the y-axis and the corresponding value of the regularization parameter on the x-axis to see how mean square error varies with the regularization parameter. We'll follow that up by making a second plot where we add the mean square error for lasso and OLS to this visualization. So looking at my code, we're going to use this formula a lot, so I've decided to define it as a variable called formula A. Again, our label demand is going to be a function of features high temperature and low temperature, a 10th order polynomial of each term, and all the two-way interactions of those terms. First, I'm going to train an OLS model. I can train a single OLS model using the LM function, but I'd also like to compute the out-of-sample cross-validated mean square error. I'll do that using the cross-validation procedure that we've seen in previous videos with the cross-v k-fold function. I'm going to train the OLS model, then compute the root mean square error out of sample, and then summarize and get the average of all of those root mean square errors. This is going to be an estimate of the out-of-sample forecast error for my OLS model. Doing cross-validation with lasso and ridge regression is a little more straightforward. I can use the cv.glmnet function. First, I'll train this model for lasso, and then I'll train it for ridge regression. You can see I do that by adding the alpha equals 0 argument to cv.glmnet, saying that I'd like the value of the mixing parameter to be 0, which is ridge regression. I'll run all of this code. Looking at the Environment Explorer, you can now see that I have trained models for lasso, OLS, and ridge regression. I've also used the tidy function in the Broom library to create tibbles of model output from the lasso and ridge regression models. Going back to my code, what I'd like to do is create a visualization showing the out-of-sample mean square error from my ridge regression as a function of the regularization parameter. This way we can see how out-of-sample forecast error might vary as we change the value of that regularization parameter. I'll create a ribbon plot that has the high and low confidence intervals of that mean square error, followed by a line plot with the actual value of that mean square error. As is conventional with these types of plots, I'm going to use a log scale for both the x and the y-axis. I'm also going to build on this visualization several times, so I'll save it to a variable and then print it out so we can see it. Let's run all of that and look at the visualization. You can see that out-of-sample mean square error tends to be low for small values of the regularization parameter, around 10,000. And then as you increase values of the regularization parameter, out-of-sample forecast error increases and starts to level off for very large values of the regularization parameter, around 10 million. Going back to my code. Next, what I'd like to do is add a similar plot for lasso, again showing how the out-of-sample forecast error for lasso might vary with the value of the regularization parameter. I'll also add a line for the mean square error of the OLS model forecasted out of sample. Remember, OLS doesn't use a regularization parameter, so that value will just be constant. And I'll produce that using the geom h-line geometry, which just will produce a horizontal line with the specified y-intercept, which is the root mean square error from that OLS cross-validation procedure. Let's run all of that and take a look at the visualization. Looking at the visualization, remember the ridge regression model is the red line, the lasso model is the blue line, and the black line is the OLS model. The lasso model shows the same pattern that we saw in previous videos. Mean square error is large for small values of the regularization parameter, then gets smaller, and as you hit values around 10,000, it starts to increase again. An important thing to note from this is that in terms of out-of-sample forecast error from this cross-validation procedure, lasso seems to be the best, having the lowest out-of-sample mean square error if you choose the correct value of lambda. If you recall, training elastic net models is as simple as changing the value of that alpha parameter in the glmnet function. So what I'd like to do is now train an elastic net model, again using that same formula. We'll set the value of the mixing parameter to 0.1. I chose this value by looking at several different iterations of this model and figuring out that 0.1 led to the lowest value of out-of-sample mean square error. After we train the model, I'm going to plot the cross-validated mean square error for the elastic net model, along with the values for lasso, ridge regression, and OLS on a plot similar to what we saw before. Looking at my R code, first I'm going to train my elastic net model. Remember, I can do that using the cv.glmnet function. I'll set the alpha equal to 0.1. I'll then create a data frame with the model results using the tidy function. I'll then take my previous visualization. I'll add a ribbon plot for the confidence intervals around mean square error, and a line for the mean square error itself, and then I'll print out that visualization so we can take a look at it. Let's run all of that code. Looking at the visualization, the purple line is the elastic net regression. As you can expect, because the penalty is a mix of the lasso penalty and the ridge regression penalty, the mean square error from this model is somewhere in between the lasso mean square error and the ridge regression model. It follows very much the same pattern as lasso, but possibly there is a larger space where the mean square error is close to its minimum. At its lowest, the mean square error is very comparable to lasso. We've trained several models now: ordinary least squares, lasso, ridge regression, and one elastic net model. What I'd like to do is evaluate each of them out of sample on that test data that we set aside at the beginning of this video. What I'll do is I'll compute predicted values from each model. When I have to choose a lambda, I'm going to use the lambda.1se value. Remember, this is the value of lambda that's within one standard deviation of the MSE minimizing value of lambda. Data scientists tend to prefer it because it leads to very parsimonious models while still trying to keep mean square error as low as possible. After generating those predictions, I'll use summarize to compute the out-of-sample root mean square error for each model. We'll take a look at that and then decide which model we would prefer. Looking at my R code, I'd like to evaluate the fit of all of these models on the test data that we set aside earlier. So I'm going to take that test data, I'll pipe it to the mutate verb, I'll generate predictions for OLS, lasso, ridge regression, and the elastic net model. In every case, I'll use the lambda.1se value for lambda, which will get us something close to, but not exactly, the MSE minimizing lambda, favoring a parsimonious model. After computing all of those predictions, I'll compute the root mean square error using the summarize verb. Again, in every case, I take the actual value of the label, demand, I subtract off my prediction, square it, take the mean, and then after all of that, take the square root. Let's run all of that code and look at the output. Here you can see all of the output, one for each model. I've reproduced those numbers here. Ordinary least squares has an out-of-sample root mean square prediction error of 12,192,698,805. Lasso is 185,873, ridge regression 192,845, and the elastic net 188,382. Out of all of these, we'd probably prefer the lasso model because it has the lowest value of the out-of-sample root mean square error. Ridge regression and the elastic net are both pretty close, but a little bit higher. The important thing to notice is that the OLS root mean square error is very, very large, several orders of magnitude larger. This is a result of the underlying model having a lot of parameters and the OLS model being very overfit. So there's a lot of modeling tools here, and it might be good to think about when it's useful to use each of them. Lasso is best when you have many irrelevant features. Remember that it's going to shrink many of the parameters on your features to exactly 0, excluding them from your model. When many of your features aren't relevant, this is something that you'd like. Ridge regression, on the other hand, is best when you have many relevant, but also strongly correlated features. Ridge regression shrinks all of the parameters in your model, but generally not all of the way to 0. So if you have many relevant features, this way you won't be excluding them like you would with lasso. The elastic net is a compromise between the two of them. You may have many features that you think are relevant, but not all of them. And if that's the case, the elastic net might be the way to go. Very importantly, you see from this example that OLS can have very poor out-of-sample performance when there are many features. This is something you should always be cautious of when you're constructing models.